Well, hello, and welcome to my YouTube channel. It's been quite some time that well, I have embraced this medium, and in fact, it just so happens that just to dispel the exaggerated rumors about my death to my very loyal subscribers, I thought that why not give them an appearance. I can't even pretend that I have been very busy in the last few months, or week or year. I don't know that I have lost track of time, in fact, and. Well, but here I am, and it just so happens that uh, ISI was conducted in the last Sunday, and regrettably, I was very busy on Monday and Tuesday, so just couldn't find enough time to come up and solve all these problems. And in fact, I don't intend to solve all the problems of ISI 2023, but I do intend to take up the most interesting one on the paper, and that was problem number one. Uh, so but I soon realized that well, I have sort of um, kept up my promise, if even if barely, because I believe that I promised that the upper bound for this YouTube channel would be one video per week, and well, I believe that I have kept up to my promise of producing one video per week, and well, so be that as may. Going forward, now, coming to the point, it just so happens that, interesting problems are very difficult to come by, and sometimes it just so happens that ISI provides you with the opportunity. Unfortunately, I believe that there has been a significant dip in the ISI standards. It could be entirely possible that just because I have now solved the last 4 years ISI paper on a trot, so it's entirely possible that my experiences of ISI have become such that I find these problems repetitive in nature. And just not being able to see something doesn't necessarily mean that the problems are not difficult. So I will not be the best judge of the difficulty level of this paper. But having said that, I do believe from where I see is that problems aren't what they were the time I took these papers up. Anyway, so coming to this problem, this is the first problem, and this is perhaps the only better one among the problems that ISI has chosen to ask. And in fact, some of the problems were so banal in nature that you'd be very difficult. You'd be in very difficult position to say that was this part of subjective ISI paper. And I'm not even talking about the objective part because, well, that's quite pedestrian anyway. Um, so why is this problem, so to speak, unique in a way? Then that's simply because for me, at least, I had never seen a problem like this before. Uh, it's more of an Olympiad kind of problem rather than an ISI sort of problem. And it so happens that sometimes ISI problems have been traditionally a problem which you would expect in examinations like Olympiad, but this is one of them, and that's simply because I haven't seen anything like this. So sometimes it just so happens that the problem is not really difficult. I don't believe that this is a difficult problem, so as to speak, but I do believe that given my mathematical exposure, this was a very novel problem. And so when you see this problem, I really didn't have any clue how to proceed with the solution. And when you don't have any clue how to proceed with the solution, so the best thing that you do is that you start with investigation, and we are going to investigate this problem. So the first question that we're going to ask ourselves is, that's one of my cats. I believe that he had some sort of convulsion, or maybe this mathematical gyan, and he couldn't digest all of it. So yeah, so one sort of thing which we can always begin with such questions is begin with investigation. That what sort of number, when raised to any integral power, will give you a number whose number of digits is always odd. So, well, you can see that one-digit numbers are ruled out, and that's simply because 9 squared is 81. 81 is a two-digit number. 8 squared is 64. 7 squared is 49. Two-digit number. All the way up to 4 squared, 16, two-digit number. Well, 3 cube is 27, two-digit number. 2 to the 4 is 16, two-digit number. And you can see that the examiner is a bit masochist, because they could have given us n greater than or equal to 1, and we would have held on to n equal to 1, And that would have been our moment of joy of finding a number whose every power gives you a number in which the number of digits is odd. But it just seems that examiner wants to rob us of the joy of guessing the answer to be obviously n equal to 1. Never mind. Let's go to, let's go to two-digit numbers. Obviously, that's not true. And that's simply because any two-digit number to the power 1 is a two-digit number. So that doesn't work. So let's go to three-digit number. Three-digit number is simply 100, the least three-digit number at least. And as you think about 100, bingo, right? Why? Because, 10 to the power 2 is 100. It's kind of nice. And 10 to the power 100 to the power 2 is 10 to the power 4. And 10 to the power 4 means 1 followed by 4 zeros, which is number of digits is 5. So yes, 100 works. In fact, 100 cube gives you 10 to the power 6, which means 1 followed by 6 zeros. So number of digits is 7, odd. And so on, like 100 to the power 4 gives you 10 to the 8, 1 followed by 8 zeros, odd. In fact, 100 to the power any integer n, it gives you 10 to the power 2n, which means that 1 followed by 2n zeros, number of digits 2n plus 1, odd. Very good. So 100 is one such number. And if you think about it, then 1000 is another one such number. There is nothing special about 100, which 1000 doesn't have, 10,000 doesn't have. Sorry, I said 1000. I should have said then 10,000. 10,000 does have the same property. There is nothing special about 100, which 10,000 doesn't have. And that's simply because this number is 10 to the power 4. And you can keep on doing this. Similarly, number like 10 to the power 6 will have the same property. And so we claim that all the numbers of the form 10 to the power 2m have the following property. And well, proof is kind of trivial, if you like. Trivial. Let me do the proof anyway. So you raise it to any power n rather, and you get 10 to the power 2mn. So it means that 1 followed by 2mn zeros. So number of digits is 2mn plus 1, which so total number of digits is odd. Right. So there we are. So 10 to the power 2mn. So that's kind of nice. That's not bad, in fact. Yeah. Moving on. So when we move on from here, and when we talk what next is possible. Now, if you think about it, so does 1000 have the same property? And immediately the answer would be no. 1000, 10 to the power 3 to the power 3 will give you 10 to the power 9, which has 10 digits in it. Number of digits is odd. So you'll realize that 10 to the power 2m plus 1 is not a nice candidate. And whenever you raise it to an odd power, the number of digits that you'll get is even. And what are the other numbers that we can look for? At this point, I was absolutely certain in my solution that this is the only kind of numbers that we are going to get, which is a form of 10 to the power 2m. And you know what? That's a fundamental difference between recreational mathematics, problems like these, and pure mathematics or research mathematics, which means that you are pursuing a problem, the answer to which you don't know, right? Because of the fact that I knew, by virtue of the fact that this problem was asked in a competitive examination, which was supposed to be solved in a fixed time, I could hazard a guess that there will be no more numbers. You couldn't have, we couldn't possibly get a number like 1759. And 1759 is another such number whose every power gives you another number in which the number of digits is odd. And if that is actually going to happen, then it's an absolutely brutal problem and a very cruel one at that. And I'm hoping that examiner is not so cruel to trust you with these kind of stuff. So that's a fundamental difference between recreational mathematics like this and applied mathematics like, not applied, in fact, pure mathematics or research mathematics, in which you don't know the answer to the problem. In fact, you don't even know that an answer exists. You don't even know that, do you have the requisite tools to solve the given problem? And that's what sometimes make research mathematics very intimidating, very challenging, very frustrating. and at the same time, infinitely more interesting than recreational mathematics, because I shouldn't have known this answer. The only thing which told me that this should be the only case is that because this was asked in a competitive examination, which had a fixed time limit to solve, right? That's my only claim to guess that these are the only kind of numbers 10 to the power of the form of 10 to the power 2m, which will have the following property. So now we're going to claim that. And by the way, like we have already agreed. So before we make this claim, we have already agreed that 10 to the power, any number of the form 10 to the power 2n plus 1 doesn't have this property, because if you raise it to any power m, you get 10 to the power 2mn plus m, right? And if you take, well, m to be odd, so you'll get that the number of digits are going to be even. And so this doesn't work, right? So these kind of numbers don't work. So now our claim is going to be simple, that only numbers of the form of 10 to the power 2 n have this property. So now we have to prove that, well, any number which has this property must be of the form of 10 to the power 2 n, right? So here's a proof. Well, so let there be any number n which lies in general in between 10 to the 2 n to 10 to the 2 n plus 1, something like that, right? And well, say that n has the following property, that when you raise n to any power, it doesn't really matter. It just so happens that it gives you the value of n, well, it gives you a number in which the number of digits are odd, right? So I'm obviously going to square. And what you get is that n square lies between 10 to the 4m to 10 to the 4m plus 2. Remember that n square must be a number in which the number of digits is odd. Now look at this number. This number has 4m plus 3 digits, and this is the least number of 4m plus 3 digits, right? And this is a number having 4m plus 1 digit. So all the numbers lying in between these two numbers must have 4m plus 1 or 4m plus 2 digits. Bear in mind. But n square is a number in which the number of digits are odd. So it must have, in fact, 4m plus 1 digit, because it can't have 4m plus 2 digits, right? Which forces n square to lie between 10 to the power 4m plus 1 to 10 to the power 4m, right? This implies, using the property, that n square must lie between, using the property that any power of n must be a number in which the number of digits is odd. So n must be lying between 10 to the power 4m to 10 to the power 4m plus 1 for the number of digits to be odd, right? And if you go back, then you'll get that n lies between, going back, 2m to 2m plus 1 by 2, something like that. And there is our solution. In fact, if you like, well, what I'm going to do, well, I'm going to wash, rinse, and repeat. Why? Well, because I have a bit of an exposure of mathematics to realize that this is leading somewhere, and B, I'm good at washing. So what I'm going to do is that I'm going to square this again, and what you get is that, well, n to the 4 lies between 10 to the 8m to 10 to the 8m plus 2. Now remember that every power of n must lie, must be a number in which the number of digits is odd. Now remember that this number has 8m plus 1 digits. This number is the least number having 8m plus 3 digits, which is odd. So all the numbers lying between these two numbers must have 8m plus 1 or 8m plus 2 digits. Your number can't have 8m plus 2 digits because it is even. So n to the power 4 must lie between 10 to the 8m to 10 to the 8m plus 1. And going back, you'll get that n lies between 10 to the 2m to 10 to the 2m plus 1 by 4. Right. And I'll just do it one more time and I'll say that that's how it works. Well, if you see that we are trying to narrow down where n lies. So first n lied here. This is kind of nice, but not that nice. And then we realize that there's a better bound for n than this one. Then we realize that this is a better bound for n than this one. So what I'm going to do, I'm going to square this one. And what do you get? N to the 16. N to the 16 lies between 10 to the 16m to 10 to the 16m plus 4. Or rather, I'm going to square this one, rather. So 16m plus 2. Now what it says, n to the 16 must be a number in which the number of digits is odd. This number has 16m plus 1 digits, odd. This number has 16m plus 2 digits, 3 digits rather, odd. And there's the least number having 16m plus 3 digits. So all the numbers are lying between these two numbers. So they must have either 16m plus 1 or 16m plus 2 digits. Your number can't have 16m plus 2 digits. Why? Because it's even. So your number must have 16m plus 1 digits, which would mean that n to the power 16, in fact, lies between 10 to the power 16m to 10 to the power 16m plus 1. And going back one step, so n lies between, well, there's something wrong about it, I believe. Yeah, it should be n to the power 8, not n to the power 16, sorry. Sorry about that. So we were squaring this one, so it's n to the power 8, so it's n to the power 8. So we were squaring this one, right? And we were squaring this one. So you get, well, n lies between 10 to the power 2m to 10 to the power 2m plus 1 by 8. And, well, if you like generalizing and inductively, you can prove that, or whatever. You can prove that n lies between 10 to the power 2m to 10 to the power 2m plus 1 upon 2 to the power k for every positive integer k. Now what we're going to do, now we're going to choose k so arbitrarily big that n has nowhere to hide, right? So make k arbitrarily big. And realize that n is fixed. N is fixed. And no matter how large n is, you can always make 1 upon 2 to the power k arbitrarily large comparison to n. Arbitrarily large to get n must be of the form 10 to the power 2m. And we're done. Yeah. So, well, I'm hoping you like this video. So this was only one of those, I feel like, kind of a nice problem on the paper, and everything else is very pedestrian and very mediocre, I might add. And having said that, I'll be taking one problem every day from this day forth or so, I believe. I can't possibly promise, but yeah. And in doing so, I will be violating my principle of one video per week. But in the long run, I'm pretty sure that averaged out over a long period of time, this is, I'm not going to look any better now. So that's about this video. And if you like this video, then please, as the ritual is, they say that please click subscribe and please share and please like. I'm pretty sure that you're subscribers, because I'm pretty sure that nobody's so insane to watch these videos who hasn't subscribed, because I know that those people who follow this channel have a great degree of inclination towards mathematics, and they appreciate good mathematics. And you're all very nice people, and I know many of you personally. And so, yes, there's no need to say that you should subscribe to this channel, but yeah, please share and please like. Having said that, if you can devise a different solution to this problem, I'd be very interested in hearing that solution out. Because to be very honest, I solved this problem using one more method, And that was a very clumsy one. And the reason why I looked for a better method was because that was a clumsy one. And then I sort of figured this out. And so that's it. Okay. Okay, all right. So that's about this video. And I shall see you again soon. Bye and take care.